Okay, yeah, let me welcome to my presentation, and thank you for the introduction. We'll talk about the spiking AI, and raising the question if the AI at the edge is have to be a spiking AI, means a neuromorphic implementation of it. Specifically addressing this topic by looking at monitoring and signal processing in radar to make it a little bit more concrete. And therefore, it's also one thing to start with giving the context. We saw already, 1 second, let me see. Yeah, this way. Okay. Just to motivate in the first place what kind of problem we are facing, and giving more concrete numbers to this also, that you have a better picture of what dimension the problem is. We already saw the levels which were mentioned by Geron in his talk. We have this level 1 to 5 for the advanced driver assistance systems and autonomous driving. While we today see more or less in a mass market the level 1 and some already level 2. And one strong driver is here, which is probably not that known to most of the people, is the new car assessment program, Euro NCAP, which is, you know this probably, well, looking for new cars. This is the 5-star rating, which is always advertised that the car is quite safe, and there's an increasing requirements to the scenarios you need to be able to satisfy. And this is, for example, now for a 5-star rating of 2022. Looking forward, you need to fulfill corner scenarios, so intersection scenarios, and therefore you need more sensor equipment on your car. Usually this would end up in corner radars to be able to sense in an intersection scenario better. And here you see already with the moving from level 1 to level 2, you have an increased number of sensors around the car. And if we now looking further to what comes next, we are seeing that for level 3 and especially then level 4 and 5, when it is about autonomous driving, we see that there are a bunch of sensors which need to be added to the car. Especially when you want to run the car autonomously, you need a 360-degree coverage of your sensing equipment, and this in a redundant fashion. That means LiDAR, camera, and radar, and all that need to be fused. So as a consequence, it is quite clear that at the end you end up with a humongous flow of data and a high demand on compute performance to cope with this object classification, detection and classification in these complex scenarios on this high data stream. And the the target and the need which we have here is to reduce the amount of data intelligently in every part of this chain of processing we have then in such a complex environment, and find an energy efficient way to do the computations. And to bother you even more with numbers, I want to dig a little bit deeper now also into the radar aspect, and show you what that means. So if you look at today's radar sensor, which is a so-called FMCW system, frequency modulated continuous wave radar. And here showing it's a simple example in automatic cruise control sensor. When you look at the early versions, you basically have more or less a sensor which is processing all the stuff until the drive command. That means it gives you acceleration, deceleration commands out of the sensed situation, and the objects which are classified if you have an obstacle or a preceding car which is slower and you have to slow down, or is accelerating and you can accelerate again. So if we look at such a system, so a radar sensor, we just pick a system which you would see today deployed in cars today. We're talking about let's say 3 transmitter channel and 4 receiver channel radar device. And when we look at the so-called MMIC, monolithic millimeter wave integrated circuit, you see that with 4 received channels, we will end up in a max of 400 megabit per second per channel, which ends up to be 1.6 gigabit per second data stream, which is coming out of that one sensor. Yeah? And that would be fully sufficient to do something like an automatic cruise control. When you look at the processing of that, you create in radar range Doppler maps, and here there's no reduction in the data stream. Then you detect where are objects in means of stronger reflections, and you look where they come from. This is direction of arrival computation. And doing that, you can reduce the amount of data up to 5 to 50 megabit per second, about, yeah, just to give a ballpark here. And with these reflections, which you selected then to be significant, you run an object clustering and classification to end up in an object list, where and this object list usually contains then information about here there's a car, pedestrian, a bicyclist, or whatever. In this distance with that speed and so on. And here you see already that you end up with 0.08 to 0.8 megabit per second, again as a ballpark. Yeah? And if you then take the decision, so the system takes the decision on acceleration, deceleration, for example, this few bits in per second. Looks quite okay if you look then on the data stream, because you can cope with this in a very early stage. But if we're now looking forward to the different levels, 1 to 5, we already see that moving from 1 to 2, you rather not dealing with a drive command, but you're looking for the object list for the combination. This is actually today the regular output which you deal with. So you have a higher data rate which you need to cope with, but it's not that much. When we look towards moving to level 2 and 3, there's a strong tendency, and actually effectively a need, when you want to fuse with a similar representation with camera and LiDAR, that you have to look at least at the detections. So that means the strong reflections which you selected out of the range Doppler metrics from a radar processing. And as a matter of fact, you have then from one sensor already a higher data rate which you have to cope with. So we see moving to higher automation levels, we even end up with a higher data rate to be processed. And that makes the situation certainly more worse. If we now looking to solutions to this, as I said, we need some intelligent way to deal with this. And we have some parts in this processing stages here at the end. Everybody would agree, object classification and so on. This is a classical domain for neural networks, kind of AI approaches. But you also might consider this in earlier stages of the processing, and also the monitoring of the devices for functional safety. So if we want and to give a more clearer picture also, or an estimate of what we're talking about in total, David Patterson gave at the Design Automation Conference once an estimate here. We are today dealing with level 3 capable systems with around 350 watts of computational power, so to feed the computational engine, and it is expected to go up to 1000 watts in level 4 and 5. Which means if you look at electrical cars, definitely will have a substantial impact onto the range of these cars. And one corridor to address this, or solution corridor to address this, would be neuromorphic implementations of the artificial intelligence components in the system, and certainly consider to apply artificial intelligence with this way of implementation to more stages of the overall processing, including the monitoring and functional safety aspects of such systems. The reason for this is, and what is the motivation for this is, here was already given in 1997 by Professor Maas, where he proved in its paper that the computational complexity, which can be covered by spiking neural networks, is substantially higher than with classical artificial neural networks. And there was here also an assessment on different applications by a startup, which shows that, exemplifies that with neuromorphic spiking neural networks, you might be able to address these performance needs with much lower power consumption. I, by intention, use the term "might" in this circumstance because, as you see, the advantage or the capabilities were already proven in 1997. We have now 2020, and you can guess yourself, looking around, how many solutions you see already with spiking neural networks, how much this is already deployed. So there's a lot ahead of us to make this happen effectively. We are happy to get support by national funding for this, and this is the KI-ESIC project funded by the BMBF. And here we're looking at the signal processing, which I showed you, to be addressed with spiking neural networks, and to see if we can leverage this power advantage these networks supposed to have. And going forward, again, the reason is that the information is encoded in spikes, and we have lower power consumption because these networks are generally less active. So we have few spikes which are sparse, so it's a sparse coding, and it's the asynchronous activity which you have in these networks. Here's an example for one publication which shows that these networks accomplish the same pattern recognition task with much less energy. So there are also proofs out there for concrete implementations. But what one should not forget about is that, as we haven't seen so far industrial solutions with which proved in product the application of these kind of solutions with substantially reduced power, because otherwise you would see a lot of
the moment you're
solutions.
frozen. Okay.
Huh? Yeah. Okay. But
the webinar froze, the slides froze, and your voice wasn't there. But do carry on. Let's see how it goes on.
Okay. Yeah. So as I said, you don't see so many solutions yet out there. So there's a lot of work ahead to leverage these benefits, which are obviously there, but it strongly depends also on the area where you apply it, because it requires some quite individual approaches to make this benefit happening on your concrete solution, let's say for the radar processing in this case. Moreover, it's quite important to look at additional benefits which these networks can provide. I said they are asynchronously active, and they have a low activity. So especially radar is one of these solutions where you have sensitive RF circuits, which might be disturbed by this activity of monitoring, especially if you do this digitally. The very standard situation for the sensitive circuits is today having the digital activity in the areas where you have usually no RF activities. With these spiking neural networks, you have the chance to run continuous monitoring of the device without a disturbance or much lower disturbance. So leveraging all the benefits of these kind of networks. So as a conclusion, I hope I gave a lot of motivations that this AI is not only attractive, but also necessary to deal with these complex autonomous driving challenges, and that neuromorphic solutions with their promise of a lower power consumption and potential lower disturbance of these sensitive systems are a path to cope with this problem. We have mainly the challenges ahead. That means have a functional safety to fulfill the functional safety requirements using artificial intelligence approaches, because this is rather tricky. But on the other hand, we also have the opportunity to use AI, especially to fulfill the functional safety requirements, which is somehow sounds like making the fox in charge of the hen house, but effectively is an opportunity which probably has to be looked at more closer. And therefore, it's quite essential to invent SNN solutions for functional safe AI to be able to fulfill all these promises which we put out for autonomous driving. Okay, so that would be from my side. Yeah, questions are coming later, as I think was agreed. Yeah.